So, this chapter is all math. How many of you know how to balance chemical equations? Okay, so we're going to do that first. Then we'll apply balanced equations to our dimensional analysis type problems. As soon as I get my act together. All right, so chemical changes are different than physical changes. So, physical changes, you keep the same substance, it's just in a different form. Usually it changes from a solid to a liquid or a liquid to a gas. Chemical changes actually alter the composition of matter, so you create a totally new substance. So, in a chemical reaction, atoms are going to rearrange, transforming your original substances into different substances, but we must obey the law of conservation of mass. And I know that y'all know what this law is because it's about the only law y'all knew from chapter 1. Because you just wrote that for the answer to everything. So, the law of conservation of mass just says mass can't be created or destroyed. That's why we have to balance equations. So I've written a lot of words there to kind of simplify that. All right, so this is what a chemical equation looks like. Here on the left, these are my reactants. I'm sure y'all know this, but I've had in the past, in Chem 2, we do a lot with this. And one day someone said, well, how do you know which one's the reactants and which one's the products? At that very moment, I thought I'd failed at life. If you go to Chem 2 and you don't know where the reactants or the products are, we got problems. So, reactants on the left-hand side, products on the right-hand side. In this equation, it's actually already balanced. There's an understood 1 here, there's a 2 here, 1 here, 2 here. So if I were to read that and put that into words, I would say 1 mole of CH4 reacts with 2 moles of oxygen. It yields 1 mole of CO2 plus 2 moles of water. Okay. You'll also notice that I included what phase each of these substances are in. So in this example, they're either in the gas phase or liquid phase. They could also be in the solid phase, so it would be an S, or AQ, which just means aqueous, and that just means it's dissolved in water. Let's see if I covered everything. Yes. All right, so the very last bullet under writing and balancing chemical equations says, the study of the numerical relationship between chemical quantities in a chemical equation is called stoichiometry. So essentially, that's what this whole chapter is. It's about stoichiometry. Okay. So let's balance some equations. The first 3 examples are the only 3 examples I have for balancing equations. On those notes I just handed out, it is given to you in words. You have to form the chemical equation. Okay. So the number 1 reads, write a balanced equation for the reaction between solid cobalt-3 oxide and solid carbon that produces solid cobalt and carbon dioxide gas. So you still don't know how to name or how to get a formula from a name. You're not doing well today. All right, so cobalt-3 oxide, what is its formula? Yep. It said it was solid. I'm going to put the S behind it. Then that reacts with solid carbon. Solid carbon is just C by itself because carbon is not one of the 7 that exist as a diatomic. It's just by itself. Okay, and then the products, cobalt solid, again, just cobalt by itself, solid form, plus carbon dioxide gas. All right, so now we've got to balance it. When I say balance it, I mean that I need the same number of moles of each element on both sides of the equation. Okay, so the way I generally do it is I form a little table. I divide it into 2 parts, my reactants, my products. I list each element that occurs in this equation. All right, then from there, I take a count on how many I have on each side. So if I look at cobalt, I have 2 cobalts on the reactant side. So I'm just going to put a 2 here. I have 3 oxygens and 1 carbon. Okay, now let's do the same thing to the product side. I have 1 cobalt, 2 oxygens, and 1 carbon. According to the law of conservation of mass, I have to have the same number of each of these on both sides, which I clearly don't. So we can't go in and change our subscripts. So instead we have to add a coefficient out in front of each of these. So the first one is pretty easy. I have 2 cobalts here, only 1 there. Well, it looks at first glance that I would just add a 2 right here. But then when I get to oxygen, I have 3 on the reactant side and only 2 on the product side. The easiest way is going to be to add a 2 here and a 3 here, so that they both become 6, right? You'll see that. 2 times 3 is going to give me 6 oxygen. 3 times 2 gives me 6 oxygen. But by doing that, I've now changed the number of cobalt on this side, number of carbon on that side. So we need to backtrack. I now have how many cobalts here? Yep. How many carbons there? Yep. All right, so let's go back here. We need to erase this 2, make it a 4. Then oxygen's good, then carbon. I have 3 on product side, 1 on the reactant, so I just need a 3 over there. Yeah. So that's the balanced equation. All right, number 2, y'all try to write out just the formulas of the words given. Let me go get a better blue marker. All right, number 2 is the worst type of equations to balance. This is a combustion reaction. I actually told you that in the problem. But combustion reactions all look the same. They have some carbon-hydrogen species that's combining with oxygen, and it always forms CO2 and water. Always. That's what a combustion reaction is. They're the worst to balance. So let's go ahead and make our table. 4 carbons, 10 hydrogens, 2 oxygens. 1 carbon, 2 hydrogens, 3 oxygens. I'm going to show you 2 different ways to do this. First way, basically what we did just a second ago, just the ending will be different. So let's go ahead, take care of carbon. When I do that, I'm going to put a 4 in front of CO2 so that I get 4 carbon on the product side. Then before I recount my oxygens, I'm going to go ahead and take care of hydrogen. Okay, I have 10 on this side, 2 on this side. What coefficient needs to go here? Yes, 5. Now that gives me 10 hydrogen. All right, now let's go back. Let's recount our oxygens on this side of the equation. I have 8 plus 5. What is that? Yep. All right, so everything is balanced except oxygen. Is there any whole number that I can put in front of O2 to get 13? No. Okay, so what you would do is you would do 13 over 2, but you can't leave it like that. You can never have fractions in your balanced equation. So if you did this, you'd have to go through, multiply everything by 2 so that this 2 canceled. Do y'all see why I did 13 divided by 2? Because 13 divided by 2 times 2 gives me 13. Okay? So go through, multiply everything by 2. Up here in blue, that would be my final answer. If you can ever reduce the coefficients down, always do that. Like if they're all a multiple of 2, go through and reduce them down. Here you obviously can't, but sometimes that will happen. So this is how I've always done, or how I've always balanced combustion reactions, but there is another way. Oh, why did I do that? All right, I'm going to erase all the blue. All right. Another way to do this is take the number of hydrogens that you have on this side of the equation So I have 10. Put that as your coefficient in front of water. So I put a 10 right there. All I did, took this number, put it in front of water. Then come back over here and balance out your hydrogens. So it should always be a 2. Because there's always going to be water on that side. Okay. Now count everything up. Recount. So I've got 8 carbons, 20 hydrogens. I didn't change oxygen. I still got 1 carbon, 20 hydrogens, 12 oxygens. Alright. Alright, well, let's balance carbon. I need an 8 right here. So that's going to change my oxygen number again. So what do I have for oxygen now? 16 plus 10. 26. I have 26 on that side. I only have 2 on this side. What do I need right here? 13. So you get the same thing. You just don't have to deal with your fraction. So you pick away and do it. All right. Any questions about number 1 or 2? All right, let's do number 3 real quick. Take a second and try to write out the formula for each of the words given. When you get done, check your answer. Alright, so here's the equation. I have it written out for you, and then I went ahead and made my chart. Notice that I've kept the phosphate ion together. If phosphate doesn't change from one side to the other words, if I have a phosphate ion on this side and a phosphate ion on this side, let's just balance it as the whole unit, okay? So don't worry about doing phosphorus and that oxygen individually. All right, so let's see. First thing I need is a 3 here. skipping over lithium for just a second. I have 1 phosphate, I have 2 over here, so I need a 2 right here. That's going to make 6. So then I just go add the 6 over here. That one wasn't too bad. I'll post y'all some more practice with balancing equations on Moodle. You must be able to balance the equation before we can do the next part, so make sure you know how to do that. Alright. Okay. Flip over to the next page of your notes. It talks about reaction stoichiometry. It's just telling you that the coefficients that we have placed outside of each compound in a balanced equation refers to the mole-to-mole ratio. Okay, that's all that is telling us. So let's go ahead and skip down to example 4 and let's apply that. So we're given this equation. All of the examples that I am going to work are already going to be balanced just to save us time. But that should really always be the first thing you look at when you get to one of these problems. Alright, so it says in photosynthesis, plants convert carbon dioxide and water into glucose according to this reaction. Suppose you determine that a particular plant consumes 37.8 grams of CO2 in 1 week. Assuming there's more than enough water to react, what mass of glucose can the plant make? Well, for every 6 moles of CO2, the plant will make 1 mole of glucose. Okay, so that's going to be our conversion factor to get from CO2 to glucose. So we have to get this gram of CO2 to moles of CO2 in order to use that equation. Conversion factor. So start with what you're given. 37.8 grams of CO2. Calculate CO2's molar mass. The molar mass of CO2 is 44.01 grams per mole. So my grams of CO2 is going to cancel. What do I use next? Maybe this right here. Right, so now I have moles of glucose. That's good, but I want grams of glucose, so I need the molar mass of glucose to get it there. The molar mass of glucose is 180.2 grams. And I solve. Somebody tell me when you get an answer. Yep. Any questions? All right, let's skip over and go to number 6. All right, number 6 says sulfuric acid is a component of acid rain that forms when SO2, a pollutant, reacts with oxygen and water according to this simplified reaction. The generation of the electricity used by a medium-sized home produces about 25 kilograms of SO2 per year. Assuming there's more than enough oxygen and water to react, what mass of sulfuric acid will be produced in kilograms? All right, so same thing as we just did, except this time we start with kilograms and end with kilograms. The conversion or the link between the two compounds we're interested in is the mole to mole ratio. For every 2 moles of SO2, I produce 2 moles of sulfuric acid. So we'll work it out. We start with 25 kilograms SO2. I'm going to convert my kilograms to grams. Then I'm going to get my molar mass of SO2 in grams. Which is 64.07 grams per 1 mole SO2. We can reduce this mole to mole ratio down, correct? To 1 to 1. Okay, then I go find the molar mass of sulfuric acid. .09 grams. And the last thing I do is I convert grams to kilograms. This and this actually cancels each other out, so you don't even have to include that when you type it in your calculator. Anybody got an answer? Yes, so 38.3 kilograms of H2SO4. Alright, so we'll stop there for today, but I want to go ahead and give you the answers to number 5 and 7 so that you can work those on your own and then check them. Then on Monday in lecture, I will start on Levantine reactant and theoretical yield. Alright, guys, have a good weekend.